Welcome to another lecture on molecules in motion. What we were talking about in the last class was discussing the various equations which we had derived for a particle moving in a medium. We said that these particles which we have derived the expressions for can be moving in a electric field, or it can be non-charged particles without a electric field. So, what we were essentially trying to establish is we had talked about motions of particle through the kinetic theory of gases. What we had derived through the kinetic theory, we were trying to extrapolate for the system which were charged, and eventually we established relationships which were applicable for charged molecules and ions or whatever to neutral ones when there was no application of electric field. So, the equations which we had derived considering the particles to be charged, and we were trying to establish a relationship with that of non-charged particles, were essentially three. The Einstein's relationship, where we were trying to establish a link between the diffusion coefficient d and the ionic mobility. If it is not a ionic particle or a charged particle, then we talk about the mobility as such. Similarly, we further modified the Einstein relationship, and we got the Stokes-Einstein relationship to have a link between the diffusion coefficient d and the viscosity of the medium. And finally, we had talked about the Nernst-Einstein equation. A relationship is between the diffusion coefficient and the ionic conductivities lambda, where these are the particles which were supposed to be charged, and if they are not charged, we do not need to separate them out into the positive and negative ions. We overlook the charge associated with it. So, let us recapitulate what each of the term is representing in each of the equation. In the Einstein relationship, the d, capital D, is the diffusion coefficient of the ions or particles if they are not charged. U is the mobility of the ions if they are charged, and if they are not charged, they are just the velocity of the particles. If they are not charged, then we do not have the z, the charge of the ion which is associated, and F is obviously the Faraday constant. The K here is the Boltzmann constant, kappa naught is the viscosity of the medium, A is the radius of the ion or a particle in that particular medium, and here this was the Stokes-Einstein relationship, and then we had the conductivity of the electrolyte, which was summation of the various charge numbers, that is the stoichiometric coefficient or the numbers of formula units of a particular charge cation or anion of a particular electrolyte, into the charge square of that ion into the diffusion coefficient of each of the ions. Similarly, for the anion part, this is the number of formula units of the anion which is generated from the electrolyte. This is the charge of the anion, and this is the diffusion coefficient of the anion. F here is the Faraday constant, R is the gas constant, T is the temperature in Kelvin. So, these relationships we have established, which can be more or less established through experimentation through measurement of conductivity. We will talk about the conductivity measurement towards the last of the lectures. What we have to recapitulate is the Walden's rule, which we had discussed in lecture 26 in quite detail. The empirical observation was that the coefficient of viscosity eta into the molar conductivity of the electrolyte, if they are the product of this is approximately a constant for the same ion in different solvent. We have seen that we discuss also various exceptions to this, but more or less we can assume the same ion and at different solvent, the product of the viscosity coefficient and the molar conductivity should be approximately a constant. So, this is what we had taken in the previous lectures. Now, let us justify as to how do we get this. From the Nernst-Einstein equation, if you remember the Nernst-Einstein equation, what we had a relationship between the conductivity of the electrolyte and the diffusion coefficient, right. So, here we see the conductivity of the electrolyte is directly proportional to the diffusion coefficient. So, according to that, this relationship gives us the fact that the molar conductivity is directly proportional to the diffusion coefficient of the particles in the medium. Then again, from the Stokes-Einstein relationship, what we had, this is the Stokes-Einstein relationship. From here we had the diffusion coefficients of the particle in the medium was inversely proportional to the viscosity coefficient of the solvent. Okay. So, here we have the diffusion coefficient is inversely proportional to the eta naught, the viscosity coefficient of the medium. From here we have the conductivity is directly, molar conductivity of the electrolyte is directly proportional to the diffusion coefficient. So, what we have d in both the terms. We have d in both the terms. If this is proportional to d and d is proportional to 1 by eta, then what can we say? We can say that lambda, that is the molar conductivity of the electrolyte, should be inversely proportional to the eta, the coefficient of viscosity, or in other words we can say, this is the relationship we have written, or other words we can say, if we multiply eta with the molar conductivity, then it should be a constant. This is what is implied in the Walden's rule. So, Walden's rule we had taken previously. What we have established now is from the relationship which we have established previously, the Nernst-Einstein relationship, from where we had the molar conductivity was directly proportional to the diffusion coefficient of that particle in that medium. Again, from Stokes-Einstein relationship, we had the diffusion coefficient of the particle inversely proportional to the viscosity of the solvent medium. So, from these two relationships, we conclude through further from this proportionality chain, we further confirm that lambda, that is the molar conductivity of the particle of the electrolyte, will be inversely proportional to the viscosity of the solvent medium. We can write eta naught to make it more clear, because we are meaning the viscosity of the solvent medium. So, eta naught, you can put eta naught here, you can put eta naught here. So, the eta naught into the molar conductivity of the electrolyte should be a constant if there is no exceptions associated, and this implies that what we have talked about previously, we are verifying that by the Walden's by the equations we have derived, and that is what we know as the Walden's rule. The usefulness of the Walden's rule, however, gets complicated or it is lost due to the solvation effect, because you see in both the relationships which you are having, you have a hydrodynamic radius associated and the viscosity coefficient which is associated. So, if you have the hydrodynamic radius, that means the radius of the ion when they are in a particular solvent medium will change when you are changing the solvent. because the degree to or the extent to which the ions get solvated in different mediums are different. This also we had taken up in the previous lecture 26-27, how if we are having a water system or if we are having a non-aqueous system, how the hydrodynamic radiuses are changed because of the extent of solvation. We had talked about HCl being a very good a very strong acid when taken in water medium, aqueous medium, and how it does not behave as a very strong acid when taken in ethyl alcohol. So, this is the reason why we have exceptions to this Walden's rule, because of the extent of solvation of the ions in the various solvent systems, and that is the anomaly we see, and hence the Walden's rule at times does not give you a constant, because the viscosity of the solvents will change with different medium. So, one factor contributing to the discrepancy of this being a constant is because of the viscosity of solvent changes with different solvent system, and the radius of the ions which we are taking A as the hydrodynamic radius, which we had taken A is here, you see the diffusion coefficient to the Stokes law, we have A here. So, if we have A different, we will have different we have A different because of the different extent of the solvated radius in different mediums. Okay. So, this confirms or this validates the or discrepancies of Walden's rule, and how we can relate and validate through Einstein's relationship. So, this is what we have revisited in terms of the Nernst-Einstein relation and Stokes-Einstein relationship. Now, I would like to talk about few fundamental questions which may be asked when we are talking about these three fundamental equations of diffusion coefficient. Okay. This is the Fick's first law, this is the diffusion coefficient which we calculated through the Stokes-Einstein relationship, and this is also the Stokes-Einstein relationship where f has been replaced. Okay. If I have these three expressions, what the question is, what is the approximation made, or what is the limits under which we derive these following expressions. So, let us look at the various approximations we have taken while deriving these expressions. First one is the Fick's first law of diffusion. Fick's first law of diffusion in any one direction or in one dimension, written in terms of the concentration. In this equation we had, if you remember, this concentration term was initially a activity term, which we took as concentration, applying to the conditions that the solution behaved ideally. That means, it was a very dilute solution, under which condition the solution could be taken as behaving as ideal solution. So, the concentration terms were replaced, the activity terms were replaced by the concentration terms in this equation. If you remember, in a solution which is not uniform, the activity was supposed to be depending on the position. This is what we had derived, and the thermodynamic force which we had taken, if I will not revisit that, but I will just mention here. Please look up the lectures if you are having any doubt. So, the thermodynamic force, when we say the solution is non-uniform, is justified when the activity of the particular species is dependent on the position where it is. So, if that is position dependent, that for a given temperature and pressure condition, then the thermodynamic force which is driving the movement of the motion of the particles in the medium will be nothing but minus R T d ln A by dx, okay, at constant temperature and pressure. And we had taken this approximation that we replace this activity in terms of the molar concentration for the conditions when the solution is very dilute, and if the solution is very dilute, we say that it is behaving ideally, and we replace the activity in terms of the concentration and activity coefficients to be 1. So, the activity could be replaced by concentration only when the activity coefficients tend to 1 in under very dilute condition or ideal condition. So, this is the concentration terms which we had written. If you remember, we had written how we had written this equation. This was written in terms of the 1 by dy into dy dx. This is what we had written by simplification. So, minus R T by C into the gradient in concentration. So, this was the driving force, thermodynamic force involved, and the assumption which we had in the Fick's first law when we are replacing activities in terms of the concentration was the solution was very dilute. So, the first assumption for this equation to be valid was the approximation that the solutions behaved ideally, that means the solutions were very dilute. What happens to the next one? This is the next one. So, in addition to the restrictions being applicable to only dilute solution as far as the Fick's law of diffusion in one dimension, the concentration terms were taken in rather than the activities. In addition to that, here what we have, here we have an additional approximation that the frictional retarding force, if you remember, the frictional retarding force was proportional to the first power of the speed of the particle. This was the speed, drift speed, and this was the constant which was obtained from the Stokes law. So, you see force is proportional to the first power of speed. What is usually force taken to be? Force is equal to mass into acceleration. It is not the first power of speed, but here we have assumed the frictional force to be proportional to the first power of speed. Okay. This is the assumption which we have taken in for this expression. So, what we have? We have the expression in this, the limitations or approximations we have taken first is that it is applicable, the Fick's first law is applicable only for very dilute solution. So, we have taken that the solution is ideal, first assumption, so that we can replace the activity terms in terms of the concentration. Second one is the frictional retarding force moving on the particle acting on the moving particle is proportional to the first power of speed of the particle instead of what is the general relationship for force. Okay. So, these two are the conditions or approximations we have taken in this relationship. What happens in the third expression? Third expression is something similar. This is the, here we have written down what f is. The f is, as you can see here, if you replace this, so these two expressions are the same, but the question which is asked is slightly different. So, here the frictional force is acting on the particle, retarding frictional force acting on the particle is taken to be the first power of speed instead of as conventionally force as defined as mass into acceleration. Next one is the Stokes Einstein relationship. What is the approximation which we have? Apart from that, the conditions of first law of diffusion, a fixed first law of diffusion, we have written in one dimension, written in terms of the concentration instead of the activities, assuming that the solution behaves ideally. Second one, the retarding force acting on the particle is proportional to the first power of the speed of the particle. This is the assumption we have taken in spite of the fact that force may not be generally not proportional to the first power of speed. And the last restriction which is associated with this one, in addition to the above two, is the assumption that the particles are spherical. See, we are talking about the particle diameter. We are assuming the particles are hard spheres and they have a definite diameter or definite size. So, in this expression what we have put up the 3 assumptions. For each of them you can now identify this is only for movement of gradient of movement of particle against concentration gradient, where we have replaced the concentration term in terms of the instead of the activities, assuming the solution is behaving ideally. Here we have taken apart from taking the solution to be behaving ideally, where we are replacing the activity terms with the concentration terms, we have also introduced that the retarding force acting on the particles is proportional to the first power of speed. In the third one, what we have taken, in addition to the solution being applicable to only dilute solution, where the fixed law of diffusion in one dimension, where the terms of activities have been replaced by concentration. In addition to the fact that the frictional force or retarding force acting on the particle is proportional to the first power of speed, what we have additionally put in is the assumption that the particles are spherical. If the particles are spherical, only then we apply A, the radius of the particle is the of the particle which is having of a definite spherical shape, right. So, these are the 3 equations and the assumptions associated with them. I hope you understand and recollect when you write them. Now, we move on to the discussion further after the first law of diffusion, where particles move through a medium due to concentration gradient. We now discuss the time dependent diffusion processes. That means, you understand what do you mean by time dependent processes, diffusion processes. We are talking about movement of particles in a fluid medium, in a liquid medium. So, what happens is what is of interest is to see how the inhomogeneities of the particles in the medium spread with time. So, you have if you see certain processes like when you are adding a colored liquid into a solution, how fast and how quickly they mix and how they diffuse through the medium. You can do that experiment, or you have done that experiment from your childhood. You understand how this liquid spreads or the particle spreads through the medium. So, what we are interested in this part of the discussion is we are trying to put in another diffusion equation, which is slightly different from the Fick's first law of diffusion. Fick's first law of diffusion is only movement of the particles considering the concentration gradient. Now, what we are going to discuss is the time dependent processes, how the diffusion process depends on time. So, how the inhomogeneities of particle in the medium spreads, or what do you say, it propagates when we have change in time. So, our aim here will be to obtain an equation, to write down an equation for the rate of change of concentration of particle in a inhomogeneous region. Okay. So, what we are writing, our aim is to obtain another equation where differential equation, where we are going to relate the rate of change of concentration of a particle in a inhomogeneous medium. So, what happens, for example, in the concentration distribution in a solvent to which solute is added. Okay. When you have a solvent, the concentration distribution, when you are adding a solute to the medium, what happens? The particles diffuse. Okay. The focus is on the description of the diffusion of the particles. Sometimes we can take physical examples. Suppose you have a rod or a bar of iron. Now, you have a heat source at one point. What you have? You are heating the bar from one point. If you keep heating the bar, what happens? And after some time, the bar gets heated up. After some time, you withdraw this heat. What happens? The bar is going to now reach a steady temperature, and the temperature will be uniform all throughout. When you are heating at the bar, initially the initially the temperature of the point where you are heating the bar is maximum, and the particles the particles which are of high energy is not yet reached to the other end. So, you will have a inhomogeneity in the temperature of the bar, but as soon as you remove the heat source, what happens? The bar gradually tries to equilibrate, and you would have a thermal equilibrium, and the temperature reaches a steady condition, and it will be same throughout. So, similar to those arguments which applies to the diffusion of physical properties like temperature, we are going to look into how the concentration distribution can occur in a solvent medium when you are adding a solute. So, this is what we are going to be looking into today. And for the next class, what we have looking into is a central equation to determine the rate of change of concentration of a particle in a inhomogeneous region given by diffusion equation. This is called as the fixed second law of diffusion, and the fixed second law of diffusion relates the change of concentration at a point to the spatial variation of the concentration at that point, and we can write the equation as the change of concentration with time equal to the rate of change of concentration. Rate means with time. The rate of change of concentration at any point is equal to the spatial variation of concentration at that point. Okay. So, this is the spatial variation, and this spatial variation is in the double derivative. That means, d square c by dx square is what we are going to be looking into. This is known as the fixed second law of diffusion, where the rate of change of concentration of a particle in an inhomogeneous region is given by this differential equation, and this differential equation is the diffusion equation, and this diffusion equation is known as the fixed second law of diffusion. We will now see how the diffusion equation follows from the fixed law of first fixed law of diffusion. So, here we have say section in which we are looking into how the particles are moving. The particles are supposed to be moving under the fixed first law from high concentration to low concentration. So, if this is my area of interest, this is the window in which we are looking into having an area, and the length of this unit, if it is say x l, and this distance which we are traveling is initially was x, and now this distance, if it is l, then this new point is going to be x plus l. The concentration at this point, let it be c, and what is the concentration at this point, let that be c prime. So, what we are going to be seeing, what is going to be the flux which is going to pass through this and exit through this. So, what we are looking actually is the window which is having a volume of A into L. So, this is the area of interest. We are looking into this area or this volume element, how the flux of particles are changing in this volume element A into L. Okay. So, this is going to be guided by the diffusion coefficient, diffusion equation, and this is going to be following the how we derive this using the first law of diffusion is what we are going to see in the next class. Thank you so much.